Welcome to this presentation entitled Understanding OpenACC Directives. As an HPC engineer at CAPS Enterprise, I am glad to introduce you to the new OpenACC standard for high-level GPU programming with the CAPS OpenACC compiler. GPUs are increasingly used to accelerate scientific applications for research and simulation. To compute with GPUs, you may use dedicated APIs such as CUDA or OpenCL, or GPU-accelerated libraries such as kubeless or QFFT. However, hardware accelerators evolve faster than software applications. The use of GPUs requires explicit references in their source code, which makes the application stick to a technology. Programming with GPUs may also use directive sets. This higher level, less intrusive approach makes your code more readable and maintainable. It also enables you to write hardware-independent applications. Directive sets for parallel programming were made popular thanks to the OpenMP standard. In 2007, CAPS Enterprise has introduced HMPP, an innovative directive set for GPU programming. Today, the HMPP compiler has been extended to support OpenACC directives. Programming many core systems face the following dilemma: keeping a unique version of code and maintaining performance on various hardware. OpenACC was designed to reduce maintenance costs, preserve code assets, be independent to fast-moving hardware targets, support multiple forms of parallelism such as device, task, thread, vector, or SIMD parallelism, while being compliant with existing parallel technologies such as MPI or OpenMP. OpenACC is a CAPS, Cray, NVIDIA, and PGI initiative to promote, as an open standard, a directive-based approach for programming heterogeneous many-core hardware. It has been announced during Supercomputing 2011. Since it is an open standard, it is available for implementation, and CAPS is one of the first companies to provide a fully compliant compiler. The OpenACC directives will allow you to express data and computations to be executed on an accelerator by using annotated code regions with some directives. The main OpenACC constructs are parallel, kernel, and loops regions. In a hybrid application, OpenMP directives or MPI primitives are in charge of implementing host-side parallelism, in blue on the picture. OpenACC directives are responsible for offloading data and computations from the host to the accelerator device using the PCI Express bus. In the following slides, we will illustrate how to use OpenACC on a real scientific application. This application is HydroC, which is an extract from the Ramses application, which is used to study large-scale structures and galaxy formations. To safely port this application onto GPU, we suggest the following methodology. First, profiling tools enables to detect hotspots of the application. These hotspots are the most time-consuming parts of code. From here, the Amdahl's law can estimate the potential speedup of the ported code. If there is no hotspot, or if these ones cannot be executed in parallel, you will not get any performance with GPU. Second, we start to port the code to GPU by using OpenACC directives. This is a simple GPGPU application. Results must be correct, but you may not get any performance. Finally, the GPGPU application can be optimized regarding data allocations and transfers or code tuning in an iterative process. Following the methodology, we have profiled the HydroC execution. As a result, we noticed that the HydroGoodEnough function is responsible for 97% of the application time. The goodEnough function relies on the Riemann algorithm to perform the main part of the computations. According to the methodology introduced before, we will start by porting the Riemann hotspot to GPU. This critical step will define whether the code porting project should be continued or not. To start working, here is an overview of the OpenACC model. In this host-controlled execution model, the host is responsible for allocating and transferring data from the host to the device, launching computations on the device, retrieving results from the device to the host, deallocating memory space on the device. To distribute computations, OpenACC introduces three levels of parallelism: gangs, workers, and vectors. Gangs correspond to the highest level of distributing computations, among GPU multiprocessors, for example. Workers correspond to an intermediate level and vectors to the finest. But take care, this implementation is compiler dependent. How does OpenACC handle the data? Every data, either input or output, used in ported hotspots should be accessible from the device. Since OpenACC is based on a distributed memory paradigm, these data are mirrored between the host and the device. To each of these memory spaces on the host corresponds a memory space on the hardware accelerator. Consistency of copies is ensured by OpenACC directives. How to write OpenACC directives? Use pragmas in C or special comments in Fortran. The remainder of the directive is the same for both languages. In C, directives apply on the immediate following statement, even syntactic blocks. In Fortran, pairs of directives are available to declare code regions. The loop directive is one of the main OpenACC constructs. It applies to the immediate following loop or loop nest and asks the compiler to implement it as an hardware-specific code, where the loop iteration space defines the set of independent computations to parallelize. This directive allows to declare loop private variables and arrays and reduction operations. Loops directive must be inserted in OpenACC parallel or kernel regions. The kernel's construct defines a region of code to be compiled into a sequence of accelerator kernels, equivalent to CUDA kernels. Typically, each loop nest will be executed as a distinct kernel. The number of gangs and workers can be different for each kernel, depending on the amount of computations to realize. The OpenACC parallel directive allows to parallelize a whole code region onto the accelerator. On the contrary to kernel's region, parallel regions are implemented as a single kernel, where the number of gangs and workers is constant for the whole region. Used as is, the parallel region asks all gangs and workers to execute the same code. With the help of the loop gangs and loop workers, it is then possible to distribute these computations amongst threads. Let's get back to our example. In the Riemann function, two compute-intensive loop nests may be offloaded onto the GPU. We can port progressively both hotspots with OpenACC kernel's regions. The copy clause specifies the size of the arrays to allocate and to copy from the host when entering the kernel's region. This data will be copied back and deallocated from the device when exiting the region. The OpenACC loop-independent directive indicates that the iteration of this loop are data-independent with respect to each other. It allows the compiler to generate code to execute the iteration in parallel with no synchronization. You may notice that the copy clauses are similar on both kernels' regions. These ones will allocate, copy, and deallocate the same data 2 times, introducing useless operations. This will be optimized in the next step. To avoid transfers between our kernel regions, we can declare the data must be allocated and transferred in the upper scope of the Riemann function. This can be done thanks to the data directive, which allows you to define scalar, arrays, and subarrays to be allocated on the device memory for a given code region. Data can be copied from the host to the device when entering the region. Data can be copied from the device to the host when exiting the region. To manage transfers, you may use the copy, copy in, or copy out clauses according to the input-output policy of the variables. The present or copy clauses declare data that may be present on the hardware accelerator. If the data has been already allocated on the GPU, its value will be used. Otherwise, the data will be allocated and copied onto the device. Do the data need to be initialized on the hardware? Do the data computed by the device need to be retrieved on the host? In the Riemann function, useless transfers can be avoided by specifying the kind of transfer to perform thanks to the copy, copy in, and copy out clauses. With the idea of an upper-level function that can manage the data, present clauses are inserted in order to get the value already present on the device if possible. In the I2C application, the I2Godunov function calls the Riemann function. Inserting an OpenACC data construct at an open scope from the loop enables to keep data alive over the different calls to Riemann. All the data specified, mainly arrays, are allocated and transferred only once onto the GPU. When executing the Riemann function, GPU data will be reused when available. Let's get back to our I2C call graph. We have successfully ported the Riemann hotspot. As a consequence, we have also ported all the remaining hotspots of I2Godunov function in red on the picture. The data region inserted in the I2Godunov function will enable to optimize transfers between these hotspots. It is possible to tune the execution of the loops on the hardware in our kernel's region by specifying the number of gangs and workers for different loops as shown on this example. For instance, in the CAPS OpenACC compiler, use the gang clause to distribute the iterations of the outer loop over CUDA blocks. Use the worker clause to distribute the computations of the inner loop over CUDA words. The OpenACC standard defines also a set of runtime library routines. It enables the programmer to get hardware information, to implement low-level asynchronism, or retrieve device pointers. When using OpenACC directives, first identify parallel sections of code as kernels. Ensure that the application runs well on GPU with correct results, and optimize it by specifying the input-output transfers for each kernel. You can possibly define a data region to enable data exchange between kernels without transferring them back to the host. Finally, ensure that the kernels take advantage of the architecture by specifying the number of gangs and workers to use. Here are a few examples of code porting success stories. The DNA distance application is a biomedical application. In a few weeks, a speedup of 13 was reached compared to an OpenMP implementation. With a Sobel filter application, a speedup of 24 was obtained in a few weeks with a few directives. How the CAPS OpenACC compiler builds hybrid applications. Here is an overview of the CAPS OpenACC compiling workflow. On top of the picture are the front ends, which takes C, Fortran, or C++ as input. After the standard processing passes, host and device code are insulated to follow different compiling processes. On the left, you can find the host binary compilation with your usual compiler. On the right, hardware-specific code is generated, transformed, and optimized before the backend generation. The CAPS OpenACC compiler generates a dynamic library including device codes that will be loaded at runtime. The HMPP command line encapsulates and hides all these operations in order to simplify the user operation. Once the application is compiled, the user can run it and get feedback from the HMPP runtime application that performs the calls to the accelerator device. Here's what you can observe when executing the ported I2C application. Let's focus on the steps performed when executing the Riemann function. First, you can notice the allocation and the copy of the input data from the CPU to the GPU. When all data are loaded on the accelerator, computations are launched. When computation ends, the results are copied from the GPU to the CPU and device memory space is freed. Directive-based approaches are currently one of the most promising tracks for heterogeneous minicores. It preserves code assets and helps to separate the parallelism description from its implementation. Some additional needs has been identified as the integration of the existing GPU-accelerated libraries and the user's code. CAPS Enterprise is also working on an auto-tuning feature to make code parting more efficient. This presentation has been done using CAPS OpenACC compiler. Please note that some of the functionalities shown are compiler dependent. The CAPS OpenACC compiler is available for C or Fortran applications, for CUDA or OpenCL devices. Please check out capsenterprise.com/OpenACC for purchase. For more information about OpenACC, please visit openaccstandard.org. Thank you for your attention. To see this webinar again, please visit our website capsenterprise.com/webinars. If you have any question about this presentation, or if you wish to get the slideshow, please send an email to webinars@capsenterprise.com.